Let us see next topic, a linear transformation. A linear transformation. In last term in matrix algebra course we have learned about a linear transformation x to ax with reference to Rn to Rm mapping. It is a transformation of a vector x to vector a into x. Now here we define a linear transformation between two vector spaces V and W. Okay. T from V to W, V and W are vector spaces. V and W are vector spaces. V and W are vector spaces. It is a rule that assigns to each vector x in V a unique vector T of x in W such that first is T of U plus V is equals to T of U plus T of V. U comma V belongs to capital V. And B is T of C into U is equals to C into T of U for all U belongs to V and C belongs to R. Okay. Linear transformation is what? It is a rule that assigns to each vector x in V a unique vector T of x in W such that T of U plus V is equals to T of U plus T of V. U comma V belongs to capital V, and B is T of CU is equals to C into T of U for all U belongs to V and C belongs to R. Okay. Let us take next definition. Kernel of linear transformation T. Linear transformation. For linear transformation, here I will use short form LT. Okay. Let T be a linear transformation. Means what? T from V to V is a rule that assigns to each vector x in V a unique vector T of x in W such that it satisfies these two properties. Okay. T be a linear transformation from a vector space V to a vector space W, then it is a set of all vectors. Then it is set of all vectors. Then it is set of all vectors U belongs to V such that T of U is equals to 0. 0 is 0 vector of W. This 0 is 0 vector of W. Okay. Therefore, in set notation, kernel of T is nothing but set of all U belongs to V such that T of U is equals to 0. It is the set of all vectors U belongs to V such that T of U is equals to 0. This is the definition of kernel of linear transformation. Now see the definition of range of linear transformation. Range of linear transformation. Range of linear transformation T. Okay, let T be a linear transformation from vector space V to W, then it is the set of all vectors in W of the form T of X of the form T of X, all vectors in W of the form T of X for some X belongs to V. Therefore, range of T is equals to T of X such that X belongs to V. It is the set of all vectors in W such that T of X belongs to V. In particular, if T is a matrix transformation, then range of T is a column space of A. Note this, T is a matrix transformation, then range of T is column space of A. Okay. This is kernel of linear transformation and this is a range of linear transformation. These two are very important definitions, so keep in mind that. Example, if T is a linear transformation, from V to W, then kernel of T is subspace of V. This is very simple. This is homework to you. Let us take next topic, linearly independent sets and bases. Next topic is linearly independent sets and bases. Linearly independent sets and bases. Let us see first definition of linearly independent set. Definition: an indexed set of vectors, V1, V2 and so on up to Vn in a vector space V is said to be linearly independent, if the vector equation C1V1 plus C2V2 plus and so on plus CnVn is equals to 0 has only a trivial solution, C1 is equals to C2 is equals to C3 is equals to and so on up to Cn is equals to 0. The set of vectors that is not linearly independent, the set of vectors that is not linearly, or set of vectors that is not linearly independent is linearly dependent. The set of vectors which is not linearly independent is linearly dependent. That is, the vector equation C1V1 plus C2V2 plus and so on up to plus CNVN is equals to 0 has a non-trivial solution. Has a non-trivial solution. Okay, this means what? The constant C1, C2 and Cn not all 0. Okay, see here, this set of vectors, when we say that this set of vector is linearly independent, if the vector equation C1 into V1 plus C2 into V2 plus and so on Cn Vn is equals to 0 has only a trivial solution, means this vector equation has only trivial solution, that is C1, C2, Cn all are 0. If the set of vectors is not linearly independent, then it is linearly dependent, means if this vector equation has a non-trivial solution, means C1, C2 not all 0, then we say that this set of vectors is linearly independent. Again here write down, that is, the coefficients C1, C2 and so on Cn are not all 0, such that the corresponding equation is satisfied. Corresponding equation is satisfied. Such that the corresponding equation is satisfied. Okay. I hope all of you understand the definition of linearly independent set and dependent set. Now let us take one theorem. An indexed set V1, V2 and so on up to Vn of two or more vectors with V1 is not equals to 0 is linearly dependent. V1 is not equals to is linearly dependent if and only if some Vj which is greater than 1 is linear combination of preceding vectors V1, V2 and so on up to Vj minus 1. Okay. This set of two or more vectors with V1 is not equal to 0 is linearly dependent if and only if for some Vj, j is greater than 1 is a linear combination of preceding vectors. Means Vj can be written as, there exist scalars C1 V1 plus C2 V2 plus and so on, Cj minus 1 Vj minus 1. Vj can be written in this form. Okay. Let us write down some useful statements to solve the problem. First is, a set containing single vector V belongs to Rn is linearly independent if and only if V is not equals to 0. Means any non-zero vector is linearly independent. It's obvious. If you take linear combination K into V is equals to 0. V is not equals to 0, that implies K is equals to 0. So always keep in mind that any single non-zero vector is linearly independent. Second is, a set of two vectors in Rn is linearly dependent. For linearly dependent, I will write LD, and linearly independent, ILI. If and only if one of the vectors is multiple of the other. If and only if one of the vectors is multiple of others. And third one is, any set containing zero vector is linearly dependent. Any set containing zero vector is linearly dependent. Okay, any set containing a zero vector is linearly dependent. Okay. These are three useful results which we will use for solving problems. Okay. Now let us take example. Show that the subset S is equals to vector 3, 2, 3, vector 1, 1, 1, 0, 1, 1, 0, 1 of R3 linearly dependent. Okay. First of all, we write the vector equation. If vector equation C1 into 3, 2, 3 plus C2 into 1, 1, 1 plus C3 into 1, 0, 1 is equals to 0 has only the trivial solution, then set S will be linearly independent. If this vector equation has only trivial solution, then set S will be linearly independent. And if this vector equation has a non-trivial solution, then set is linearly dependent. Okay. Now we write the following homogeneous system. We write the following homogeneous system. Okay. So that system will become 3C1 plus C2 plus C3 is equals to 0, 2C1 plus C2 plus 0 C3 is equals to 0. Next is 3C1 plus C2 plus C3 is equals to 0. Okay. The determinant, if you take coefficient matrix of this system, suppose call this equation star, the determinant of coefficient matrix A. The determinant of coefficient matrix A, that is determinant of A is 0. Here we will calculate determinant of 3, 1, 1, 2, 1, 0, 3, 1, 1. This will be 3 into 1 minus 0 minus 1 into 2 plus 1 into 2. 2 minus 1. This will be 3 minus 1 minus 2 is 1. Here is minus 3. So we will get 3 minus 2 minus 1. This will be 0. So determinant of this matrix A is 0. Therefore, equation star has a non-trivial solution. Therefore, set S is linearly dependent. Okay. If this matrix A has if determinant of this matrix A is not equals to 0, then equation has a trivial solution. At that time, set S is linearly independent. This is one method, or you can take this coefficient matrix and you will reduce it in row echelon form and find the values of C1, C2, C3. If that values are found and not all 0, that time also this set is linearly dependent. But this is a best way to check whether set S is linearly dependent or not. Let us take one more example. Show that the set of vectors T is equals to matrix minus 2, 0, 1, matrix minus 1, 0, 1 in R3 is linearly independent solution. The set T is linearly independent. As the vector equation as the vector equation plus E2 V2 is equals to 0, where V1 is equals to matrix minus 2 0 1, V2 is equals to matrix minus 1 0 1, has only the trivial solution. Here has only trivial solution. Has only trivial solution. This is very simple. C1 into minus 2 0 1 plus C2 into minus 1 0 1 is equals to 0 0 0. Okay. So this will become minus 2 C1 minus C2 is equals to 0. 0 C1 minus plus 0 C2 is equals to 0, and C1 plus C2 is equals to 0. Okay. Augmented matrix is minus 2 minus 1 0 0 0 1 1 0. Okay. It's equivalent to, or here we will perform a row operation R2 3. So we will get minus 2 minus 1 0 1 1 0 0 0 0. Okay. Obtain row echelon form of this matrix, and from, okay, just see what happened. Okay, again interchange. It's very simple. Keep at solve this. If you are able to find the values of C1 and C2 and perform a row operation R1 2, so we will get a matrix minus 2 minus 1, you will get a matrix 1 1 0 minus 2 minus 1 0 0 0. Okay. Now perform a row operation. Here we require a 0. For that purpose we will perform a row operation R2 plus 2R1. So matrix will become 1 1 0 minus 2 plus 2 is 0 minus 1 plus 2 is 1, and this is 0. Okay, 0 0. So from this matrix observe that you will get C2 is equals to 0 and C1 is also 0. So this vector equation has a trivial solution. That's why this set of vectors is a linearly independent. Here we cannot find, in this case we cannot find a determinant because this matrix is not a square matrix. Okay. Okay, we will stop here. Thank you.